Swayam Prabha. Digital India. Educated India.
Students, in the last part of the 4-phase ternary equilibria, we are going to discuss about the type 2 equilibria in the ternary phase. In case you have forgotten, let me just remind you that type 1 is what? Type 1 is the ternary eutectic, where liquid get transformed to 3 solid phases. Type 2 is quasi-peritectic, where liquid reacts with alpha forming two phases beta and gamma, and type 3 is ternary peritectic, where alpha, beta and liquid reacts and form gamma. So, this we call ternary eutectic, this is called quasi-peritectic. I will tell you why it is quasi-peritectic and how we can analyze it today in the lecture, and third one is known as ternary peritectic. If you recall, I have a detailed discussion on ternary eutectic, and in the last lecture I discussed about ternary peritectic. So, today we are going to discuss about the quasi-peritectic. So, as you know, this is reaction, that is liquid plus alpha going to beta plus gamma, is a mixture of eutectic and peritectic reactions, correct. So, what is it is, how it is a mixture of eutectic reaction? If you look at its first part, liquid plus alpha going to any phase, whether beta, gamma, delta, is a peritectic reaction, right. On the other hand, when liquid plus alpha react and form two phases, it will be eutectic type. So, that means this is a mixture of both eutectic and peritectic type, and that is why it is called a quasi-peritectic reaction. So, to describe it on a ternary phase plane, it has got, it is a 4-phase equilibria. So, therefore, it will be represented by a trapezoid or trapezium, and the corners of a trapezium will be alpha, beta, gamma and liquid. That is what is shown in the middle, okay. And this happens at a fixed temperature. Also, it is an invariant equilibrium. So, that means compositions of all the phases alpha, beta, gamma and liquid are fixed, you cannot change, because degrees of freedom is 0 in a ternary system when 4 phases are coexisting. So, what happens actually? This ternary 4-phase equilibria is always preceded by 2-3-phase invariant monovariant reactions, or 3-phase monovariant equilibria. One is alpha, beta and liquid, second one is alpha, gamma and liquid. So, these two invariant equilibria must exist prior to the 4-phase equilibria. And not only that, if you see the decrease in temperature, as you decrease the temperature, the exit from the ternary 4-phase equilibria will happen with 2 3-phase equilibria again. One of them is alpha, beta and gamma, other one is beta, alpha and gamma, correct. So, the characteristic features, the important characteristic feature for such a kind of quasi-peritectic 4-phase equilibria is that there has to be 2 monovariant reaction which will precede the invariant reactions, correct. That is the most important criteria. There has to be 2 monovariant reactions or equilibria preceded by, and these 2 monovariant reactions can be peritectic and eutectic type, or both of them can be eutectic type. What is the meaning of that? As you see here, there are two monovariant reaction present at temperature higher than the invariant plane. This is the invariant plane, these are the two monovariant reactions, correct. One is alpha beta liquid, other one is alpha beta gamma liquid. What I am saying is that these two can be either peritectic plus eutectic or eutectic. What is the meaning of that? If it is peritectic plus eutectic, that means liquid plus alpha will react and form the beta phase for the first 3 phase equilibria. The second one, liquid will transform directly to gamma plus alpha, correct. That is what we are saying. Otherwise, both of them can be eutectic also. So, basically if you look at properly, liquid plus alpha going to beta is what? Is a monovariant peritectic reaction in ternary system. Ternary are 3 components, 3 phases present. So, therefore, C minus P plus 1, C is 3, P is 3, cancel and 1 will remain. So, degrees of freedom will be 1. Now, in this case, liquid reacts with some primary alpha and forms the beta, and this reaction, that is formation of beta by reaction between liquid and alpha, continues till it reaches the ternary quasi-peritectic plane. In the space model I will show that, and at this temperature, the ternary quasi-peritectic plane, which has a fixed temperature, this liquid and alpha will react and it will deposit beta plus gamma, correct. I hope it is clear. So, that is why actually we have alpha plus beta plus gamma below the ternary univariant reaction plane, and some liquid will remain which will form some other eutectic phase at lower temperatures. So, that is the unique thing. So, because you have to have 4 phase equilibria reacting like liquid plus alpha going to beta plus gamma, correct. If you can see properly, liquid plus alpha going to beta plus gamma. So, this reaction must be preceded by a peritectic type of reactions at higher temperatures, and that is the important characteristics of this reaction. Now, let us look at how we can draw that. Well, that is not very difficult to do it. Let me just try and draw it and show you. So, first type is what we are considering is that, let us say liquid alpha beta and liquid alpha gamma are peritectic type. What I mean to say, these are the binaries we will see, and liquid beta gamma is eutectic type, right. Let me first tell you what is that. Suppose this is my space model. Oops. Let me draw it other way, otherwise it will not look nice. So, between A and B, you have a peritectic reaction. What is that? That is very simple. Liquid alpha beta liquid plus alpha, that is the peritectic reaction. Between A and C also there is a peritectic reaction, that is the liquid alpha gamma. Okay. So, what is that? Let me just draw it. Sorry. Am I clear? So, this is the peritectic reaction on the, this is alpha, this is gamma, the liquid plus alpha, right. But on the other hand, between B and C you have a eutectic reaction. So, this is the eutectic reaction, this is beta plus gamma. So, what I am asking is that if this is the binary systems, then what will be the ternary space model? That is what we are going to do. So, let us draw it first, it is not going to be a difficult task. So, I am going to use color chalks to tell you that. Okay. So, I am going to draw between A and C, first A and C using a red color chalk. This is what it is. Between B and C is a eutectic, that is easy. Okay. And between A and C another peritectic reaction. I think we should draw it little above, otherwise you cannot see it properly. Okay, that is how this thing will look like. Let me just draw what is inside. Inside thing is not very difficult to draw. So, this is one point, this is another point. So, we get this one point, this and this another point, and this, yeah, another point. So, I connect it, and point P will be the peritectic point turner inside, like this, which is, this is another peritectic and this is the another peritectic. Okay. So, then you can connect this triangle you can see the trapezoid. Okay, that is the trapezoid I am talking about it. So, it is basically like this, this, this is the trapezoid. So, this point is P, this is A, this is B, this is C, right. So, it is little bit complex, but still understandable. So, what you see here is that if there are two peritectic reactions on the two binaries and a eutectic reaction, it actually generates a ternary peritectic reaction or ternary 4-phase equilibria kind of reaction. This is this point P, this is the point P, this is A, sorry, this is the point P, B, C. This point P is basically corresponding to liquid plus alpha going to beta plus gamma. That is what I am saying. There are many systems which actually follows these reactions. At least I can give you. Okay, let me before that let me just tell you. If you look at properly, there are 4 triangles here, and these 4 triangles can be represented like this. A, B, P is basically liquid alpha beta, which is nothing but peritectic type. I have written P and peritectic P, right or right, peritectic type. Then A, C, P, A, C, P. Okay, this triangle. First one is A, B, P, this triangle. Second one is A, C, P, this triangle. This is also sitting above. Okay, so this is liquid alpha gamma. This is eutectic, and then below they are all lying above. Below this you have BCP, BCP, this is lying below this ternary force plane. Okay, this is liquid beta gamma, this is also eutectic type looks like, and ABC is alpha beta gamma, correct. So, these are the 4 the 3-phase equilibrium planes which is observed, which is sitting there on this triangle. So, everything on this trapezoid, everything solidification or all the alloys will be depends on how this triangle how this trapezoid will behave, and I do not want to go into details of that. That will be quite bit complex in the sense that we have to look at how these triangles are lying on the 4-phase planes, and also we have many compositions of alloys which will undergo these 4-phase reactions. Remember that, and depending on this 4-phase reaction composition, temperature and the composition, basically the solidification pathways will change. So, there are many such systems where this can happen. I am going to show you another case. Okay, actually same things here, whether you can understand better way. So, see if you look at that A, B, C, right, A and B, A forms peritectic, and this peritectic is represented by P1, and AC forms a peritectic that is represented by P2. You can clearly see this is a peritectic. On the other hand, BC forms a eutectic which is represented by E. Now, these points which I have drawn inside A, B, C and P, correct. These points are coming basically from A is coming from the solubility limits A1 and A2 for the AC binary and the BC AB binary, right. If you extend that, they forms a point A. Similarly, B is also formed very easily from B3 and also B3 and also B1, they are joining and forming point B. Point C is also from what point C is getting from the, it is lying on this C3 A point, but from C2 and from C2, yes, and from this line which is CH. Okay, that is how the point C forms, and P is basically formed by joining EP and P2P and P1P, correct. So, if you join, that is what is shown on the board. Okay, all the peritectic reactions are joining at the point P. 2 are coming from the 2 binaries and 1 is coming from the eutectic of the binary BC. Now, it will be very easy if I take if I project everything onto the Griff's triangle. So, that is what is shown on the right side. If you see here alpha, beta and gamma phase fields are shown, and then these points A2 and A1 extended, and then we get a point A. Similarly, B1 and B3 extended, B1 is here, B3 is here, they are extended, we are getting point B, right. And C is coming from C2 is this one, C2, and also coming from C3 is this, okay, yeah, C3 is coming from the terminal horizontal limit of the eutectic on BC, that gets C, and P is basically connected between P2 and P1 and also E, these 3 points, that is how. So, this is what this inside plane is what I have drawn there, I am drawing again, okay, this is a trapezoid, you can see here carefully, trapezoid, correct. So, this is point P, this is point A, this is point B, this is point C. So, here you have all these planes lying, that much is very clear to you, right. That is how the things actually happens in this phase field. Now, one can actually draw even much complex diagrams where you have 2 eutectic and 1 peritectic, that is also possible. Having one can draw that. Our systems which follow this kind of things are carbon, titanium, tungsten, aluminum, magnesium, zinc. Okay. These are the 2 alloy system they form, carbon, titanium, tungsten and aluminum, magnesium, zinc. These 2 ternary systems are widely observed to follow this phase phase things, and for the first system, the ternary reaction for the first system, the ternary reaction is like this, ternary 4-phase reaction, liquid plus tungsten plus TiC going to, yes, TiC, it forms a compound and this is going to titanium. This is the reaction. Oh, this is not the reaction, sorry, something else I have written. Okay, no. This is the reaction, correct. So, that is actually quite a bit small description of this ternary quasi-peritectic reaction, and in metallic systems this has been observed prior to any eutectic or peritectic reactions in the metallic systems. So, I do not want to get into details of those metallic reactions, because this will open up a new chapter, and if you look at properly in the textbooks, there are a few pages used to describe this reaction, because for ternary most important reaction is the eutectic reaction, correct, and in many cases you find peritectic reaction, but this one is as it is between eutectic and peritectic, so that brings a lot of complexity, and many cases even we do not understand research level also these reactions. That is why we seem to overlook the importance of this reaction in the ternary phase diagrams. So, if you want to really know about details of these phase diagrams, little bit of topology needs to be understood. Topology means how these planes are appearing, that like this trapezoid which I have drawn is very difficult for you to conceive that how ABP and ACP are lying above the top of the plane and BCP and ABC is lying at the bottom of the plane. It is not easy. So, that means the trapezoid is lying at the inclined angle, that is why you see some planes at top and some planes at bottom, but it is actually a 4-phase equilibrium plane, correct. So, unlike eutectic or peritectic, this is completely different. So, with this I like to conclude this lecture. So, next two lectures, which will be the last 2 lectures of this course, we are going to take few case studies of the ternary phase diagrams. An important one will be obviously one of the important phase diagram will be ceramic one, aluminum oxide. I do not remember what is the phase diagram I have given in the syllabus, and I will discuss two metallic one is stainless steel, other one is a superalloy. So, in the next class we will start with stainless steel. Stainless steel is nothing but a ternary phase diagram between iron, chromium and nickel, and nickel superalloy is a ternary phase diagram of nickel, chromium and aluminum. Okay. So, these two ternary phase diagrams we will discuss first, and finally, we will discuss the ceramic phase diagram, which is based on aluminum oxide. Okay, thank you.